Hello, young math Padawans. It's Mrs. Angel with your lesson for today on solving quadratics. So we've done quite a bit with quadratics so far. We've done graphing, evaluating, labeling. The final part of this is solving. What does it mean to solve a quadratic? What special solutions are we looking for? These two right here. To solve a quadratic means to find its zeros. So if I handed you this quadratic and I told you to solve it, that means tell me the zeros of this function. Give me the input x that produces an output y of 0. Now, before we can actually start solving some quadratic functions and finding the zeros, let's do a quick review on the types of zeros that you can have. So it's most common when you're graphing a quadratic that your function is going to have two zeros, meaning that the parabola is going to cross the x-axis in two locations. The parabola on the left has two zeros, and the parabola on the right has two zeros. The second scenario, when you have a parabola in a quadratic function, is that your parabola only crosses the x-axis in one unique spot. That would mean that these parabolas have one zero, only one x-intercept. Now, this only occurs when the vertex and the zero are the same point. The third and final scenario is when the parabola does not cross the x-axis. In both of these cases, you don't see any points that the parabola shares with the x-axis. There are no x-intercepts in either parabola. So we would say that these parabolas have no zeros. The goal of this unit is to develop some new tools that allow us to solve quadratics, aka find the zeros, in all three forms: standard form, vertex form, and intercept form. There are different tools that we can use depending on the form that we're given. So below me, I have a list of our square roots. And in this case, we're only going to be looking at perfect squares, not irrational square roots. So like taking the square root of 10, for example. Notice here that in each of these, it's not just one solution, but actually two. Because when you take the square root of a number, it's going to produce a positive and a negative value. Let me show you why. If I were to take, for example, 4 and square it, that would produce an output of 16. However, if I were to take -4 and do the same thing, it also produces an output of 16 because we have two different inputs, +4 and -4, producing the same output of 16. Well, then it would work the opposite way. If I take the square root of 16, I need to account for both the positive square root and the negative square root. So from here on out, every time we look at taking a square root, we're going to account for both the positive and the negative. So why the all of a sudden interest in square roots? That's because in this video, we're learning about a new property of equality and a new inverse operation. Let's review the ones that we already know. Addition property of equality states that you have to add the same value on both sides to keep an equation true. That is the inverse or opposite operation of the subtraction property of equality, which states you have to subtract the same value from both sides of an equation for the equation to remain true. We also know about the multiplication property of equality, which states that you have to multiply both sides of an equation by the same value to remain true. And that is the inverse or opposite of the division property of equality, which states the same thing. However, what you divide on one side, you must also divide on the other to remain true. Now, these are the only properties of equality that we've used so far in solving equations. Now we're going to introduce a third one. When we're looking at an equation that has a square, the inverse of squaring is to take the square root of that value. So if I wanted to isolate x squared, I would have to take the square root to essentially undo that square. This is called the square root property of equality, meaning if I take the square root of one side of an equation, I also have to take the square root of the other side of the equation for the equation to remain true. Let's look at some examples. So there are three examples here of equations where I now have a square on one side, and to isolate x, I need to apply the square root property of equality. So looking at example 1, we have the function x squared equals 25, and some of you might already be able to use mental math to know what number do you square to get 25. But mathematically, to isolate x here and to undo the square, we would apply the square root property of equality and take the square root of both sides. However, if you recall, this is not just going to produce one solution because there are two square roots of 25. X in this case can equal 5, but x can also equal -5. And that is evidenced when you check both in the original equation. As you can see in the check, both 5 and -5 are solutions to the function in example 1. Moving on to example 2, we have the function x squared equals 0. To isolate x and to undo the square, we're going to apply that same property, the square root property of equality. If you recall from graphing quadratics, 0 is somewhat special because when you square 0, it only produces one unique output. The same goes for when you take the square root of 0. There is no positive and negative 0, it's just 0. So in this case, we only have one possible solution, and that would be 0. As you can see in the check, 0 is the solution here. In example 3, we have the function x squared equals -16. To undo the square, we're going to apply the square root property of equality. And from here, wait a minute, there's something fishy and a little off here. Can we take the square root of a negative value? No, this function has no solution. And if this were a quadratic, that would mean that the quadratic had no zeros. Pretty straightforward. Let's look at a couple that are a little more complicated. Now, these functions don't look like the previous ones. However, if you actually look at deep down their structure, they match the previous examples almost identically. What you have to learn to recognize is the fact that this is just a power as much as x squared or m squared or n squared. The only difference is the base of the power is a group. So the function in example 1 is quantity n minus 4 squared equals 49. And again, because that is a square, we're going to apply the square root property of equality and take the square root of both sides. From here, we're going to set up two equations because there are two square roots of 49. In the first equation, we have n minus 4 equaling 7 because that's one square root of 49. And in the second equation, n minus 4 equals -7. All we have to do is quickly solve for both by adding 4 to both sides. And one of our solutions appears to be 11, where the other solution is -3. A check would show whether or not that's right or wrong. And we can now see that these are, in fact, the two solutions, 11 and -3. In example 2, we have the function quantity n minus 4 squared equals 0. Because the left side is a square, to undo a square, we apply the square root property of equality. What's different about the square root of 0? The square root of 0 only has one solution, meaning we're only going to set up one equation. N minus 4 equals 0. Let's solve by adding 4, just as we did in example 1. In this case, we have n equals 4. After a quick check, we can confirm that 4 is indeed the one and only solution to example 2. In example 3, we have the function quantity n minus 4 squared equals -9. Because n minus 4 squared is a square, to undo it, we will apply the square root property of equality. And that leaves us with, wait a minute, can we take the square root of a negative number? No, we cannot. So because this is a negative and there is no square root, we can state that this function has no solutions. Or if this was a quadratic, we would say that it has no zeros. That's the square root property of equality, and that's the end of today's lesson. I will see you next time.